Hi everyone, thank you for taking time to listen to this video. In this video, I'm going to introduce our paper entitled CryoRL, Reinforcement Learning Enables Efficient Cryo-EM Data Collection. Our team is from Amazon, University of Michigan, Michigan State University, Harvard University, and MIT. First, I want to take some time to introduce the motivation of the proposed method and the application background. Cryo-EM data collection is a very important aspect of a very important technique in structural biology called cryo-EM. Cryo-EM, the full name cryo-electron microscopy, is a key technique to decide the 3D structure of very important micromolecule complexes, so people can figure out the function of those micromolecules. And however, most of the micrographs the microscopy collected are not useful. And if we want to move the camera on the different locations in a very large grid collected by a microscopy, it's going to take a very long time to do long distance moving. So in this case, in the real world application, cryo-EM data collection remains ad hoc. This is because we don't have a very systematic approach to decide where are the locations we are more likely to find high quality holes. And it is not significantly better than random work on a large grid. In the picture on the left, we can see a demonstration of the hierarchy of cryo-EM data collection. First, we have the sample, and for each sample, we will observe a bunch of grids. So grids is the highest level. For each grids can be separated into different squares, and the squares can be separated into different patches. And for each patch, we can pick the whole locations where we can retrieve the micrographs. And the cryo-EM data collection process is, in fact, we move the microscopy on the different hole locations within the grid. And some of the locations will have high quality micrographs, and some of the locations will have low quality micrographs. And the cryo-EM data collections, in fact, trying to find the trajectories where we visit as many as possible high quality micrographs. An efficient navigation on different hierarchy is not a very simple problem. Given this in mind, we propose a reinforcement learning framework called cryo-EM. Cryo-EM consists of two parts. In the first part, we first train the image classification model to predict whether each whole level location has high quality micrograph. And then we train the reinforcement learning agent using the algorithm double Q network to do the high level planning for the data collection on the different hierarchy. So the actions for the reinforcement learning algorithm is the whole location where we want to move to in the next step. And the reward function design is the most critical part in this paper. We first assign a positive reward, 1.1 if the agent reaches a target hole with good quality. And the agent also receives a negative reward to penalize the movings across different patches, square, and grid because long distance moving is time costly. And we construct the feature in the following way. So first of all, we will have the prediction on the probability of whether this whole location has a high quality micrograph. So this will be a binary feature. And then we also generated some high level summary features of patch, square, and grid images to help the agent do the high level planning. And to inform decision, we also have the features to make sure that the agent could consider the high level movement, the penalization across different high level hierarchy. we also include the features on whether this is going to be the next hole is going to be in a new patch, new square, or new grid. The proposed approach could be summarized in the following figure. For each hole, first we run an image classification model to predict the quality of this hole, and then combined with the summary statistics of the grid, square, patch, and hole level features, the reinforcement learning algorithm will do the planning on the hierarchy, given the designed reward function. And we also include a technique called action elimination. This is because in our dataset, the action space can be very high dimensional, which significantly slowed down the evaluation and the training process. An action elimination process is to only consider the actions, the top 10 actions for this model. We mainly evaluate our proposed approach on 3 different datasets. Y1 dataset is a simulated dataset where all the squares, patches, and holes and micrographs are observed and evaluated within a defined region of micro-EM grid. And so this results in a fully labeled dataset. And Y2 dataset is similar to Y1 dataset. We have 3,969 micrographs with different sample and grid types. This is also a fully labeled dataset. In summary, we train our model on Y1 dataset and evaluate it on Y2 dataset. And we also have another dataset called M, where it consists of the user's daily use of microscopes in real-life scenarios from 2019 to 2022. And M dataset is mainly to test the transferability. It is not a fully labeled dataset. We first give a very brief overview of the main result in this paper. Our proposed method is called CryoRL, and we compare it with naive approach called greedy, where we greedily select holes based on the image classification quality score. And we also compare it with 2 optimization techniques called GA and SA. On the figure in the left, we can see that Cryo-EM in general select the highest number of CTF, which is the quality of the micrographs, given the total number of holes that we visit in this trajectory. For different durations, the limit on the total number of minutes we allow the agent to navigate in a grid. And in this table, we also have a summary of the cumulative reward for different approaches. And the CryoRL using DQN achieves the best result of all the different choices of durations. Notably, it also outperforms a human agent. To testify the transferability, we train our model on Y1 dataset, and then we evaluate the performance drop when we test the model on Y1, Y2, and M dataset. And the transfer probability is in generally good when we transfer the trained model to different datasets. In this page, we give some high-level visualization on the actual trajectories collected by CryoRL method. On the left-hand side, we visualized one actual trajectory of CryoRL data collection. One can see that within a patch that is visualized in this figure, CryoRL algorithm is able to select the patches that has in generally higher CTF value, meaning that the micrographs selected by the CryoRL has good quality. On the right-hand side, we have an illustration of data collection policies from CryoEM and human subject. And the size of the dots in these figures represents the quality of different squares. And one can see that cryo-EM data collection has trajectories that centered on the squares with higher quality compared to user policy. So those are the two intuitive demonstration of why cryo-EM could improve the cryo-EM data collection quality.